All right, physicists, welcome to our April 26th edition of physics, our second to last class period of physics. We are, at the moment, trying to get ourselves back up to speed so that we understand all of our previous material for the exam. Today we're going to be reviewing the Unit 2 big ideas, which are, of course, Newton's three laws, the ideas of different types of energy, kinetic energy and potential energy, and how if you have energy conservation in a system, these types of energy can be shuffled back and forth. The work energy theorem, so the idea being that the change in your kinetic energy of an object depends on how much work you do on the object. So it's establishing a sort of an equivalence between work and energy, work being your force times your distance, and then finally just a little bit on power, which is the amount of work that you're putting in the system per unit time. So those are all the big ideas that we're going to do today. Last time and last Wednesday, we talked a little bit about our Unit 1 material, our kinematics material. And as I've tried to make the point, the short answer questions on your review are literally the questions that are going to be on the exam. Different numbers, but same idea. So I want you to take the time to make sure you understand them. So for instance, here is a kinematics type of question that I put on your review. And it says, a cat lunges at a mouse. So here's an x versus t. I say, the displacement of her center of mass from the time she lunges to the time she returns to her pillow can be approximated by x equals 7t minus 3t squared. So this is a function that looks something like this, where x is in meters and t is in seconds. So the first question I ask is, how long does it take for the cat to return to her pillow? Well, if you draw a picture like this, you can see what's happening. The cat is going forward, slowing down, grabs the mouse, and then immediately begins speeding up again as she goes back to her pillow. So if you have a picture like this, it can be hard to see just from an equation, but if you have a picture, here's an x equals 0, there's an x equals 0. So all you need to do is go ahead and set x equals 0, so that 0 equals 7t minus 3t cubed. Now obviously t equals 0 is one solution, but I have faith that you can go ahead and solve for the other solution for that. Now the second question I ask you is, how far does the cat venture out from her pillow? So again, looking at the picture, here's the plot, here's the cat going forward and then coming back. And the farthest out that she gets is going to be right there. And I give you the hint, find how long it takes for the cat to stop. So the idea there is that when the cat turns around, the slope of this, or the velocity, will be 0. So if you have a position versus time, you can find the velocity versus time by taking the first time derivative. So there's 7 minus 6t. And you can go ahead and say v equals 0 to find your t. And I'll call that t stop. And then if you have that t stop, you can go ahead and calculate your x stop, which would just be 7t stop minus 3t stop squared from this. Okay, and then part C, we're asking, what is the cat's acceleration during this lunge? Well, I already have v versus t, so if I want to find acceleration versus time, it would just be the derivative of that. It would be derivative of a constant is 0. It would just be minus 6 meters per second squared. Okay, does the acceleration change when the cat is moving forward versus when the cat is moving backwards? Here the cat is moving forwards, there the cat is moving backwards. But it appears that the acceleration is the same the whole time. How can that be? Well, what it means is that when I'm going forward and I have a negative acceleration, it means that I'm slowing down. If I'm going backwards and I have a negative acceleration, that means I'm speeding up backwards. Okay, so simple problem, but as I say, all of these are worth going over in detail, so when you get to the exam, you can just, fill it out without having to sweat too much. All right, so enough of kinematics. Now we're going to go and try to explain motion. And remember, back in the day, we had the ideas of Aristotle holding sway. And Aristotle had a very sensible but wrong idea that it was forces that are causing motion. And that makes a lot of sense until you start to apply it in sort of ideal situations. So, for instance, going out to outer space, you throw a rocket and it can keep going and going and going and going if it's outside, very far away from gravitational influence. So Newton said instead, motion is the natural thing. It's natural to, if you're moving, to keep on moving. What we need to explain is acceleration. Changes in motion need to be explained, not motion itself. So this led to these Newton's three laws. Newton's first law tells us that if there's an acceleration, there's a force. Otherwise, no forces means no acceleration. You'll either just keep sitting still or you'll keep moving at exactly the same speed as you were at the beginning. Newton's second law tells us how do you move if you know what the forces are. So it says F equals ma. So if you have a net force, it causes a change in velocity. Okay, and we have many versions of this, from circular motion to accelerated motion in a line to three-dimensional, etc., etc., etc. And then the third one is the one that's the least intuitive, perhaps, but maybe the easiest to demonstrate, which is that if you have one object and another object, and you say, okay, I want to pull with one on the other, how do the forces relate? And the forces are the same. Okay, so if A acts on B, B is going to act on A with the same force. But because different objects have different masses, that can still lead to different effects. Okay, so just to say it more concretely, Newton's first law, if no force acts on a body, the body's velocity cannot change. So here we see our ball rolling down a pipe. It goes up, down, up, down, up, down, up. And then once our ball is ejected from the pipe, if there's no extra force, we're watching it from on the top of the table, for instance. If there's no extra thing pulling on it, it'll just keep going in a straight line at the same speed forever. So here's an example problem. It says, the position of a crate sliding across a frictionless surface is plotted as a function of time in the graph below. Which of the force versus distance graphs shown corresponds to this situation? All right, so what's happening in this picture? Well, I start out at x, x equals -5 or something, and I just keep going forward. So my x is getting more and more positive, and the slope is flat. It's not, well, the graph is not flat, but the slope is constant. So what that means is I'm going forward at a constant speed. Okay? So v is a constant. A then must be 0. Okay? If you have a constant speed, your acceleration is 0. If your acceleration is 0, F net equals m times a. And a equals 0 means that F equals 0. So our force here is just 0. Okay, and that's what my next slide showed. Okay, and the next idea is Newton's second law. Newton's second law says that forces act like vectors and they cause masses to accelerate. So F equals ma. That's one of your hand tattoos by now. And the units on force are newtons, kilograms times meters per second per second. Kilograms, meters over seconds squared. And what does that mean? Well, it means that if you take a 1 kilogram mass and you're just out in outer space and you push on it with 1 newton of force for 1 second, by the end of that second, the kilogram will be going at a speed of 1 meter per second. 1 meter per second per second. And if you pushed on it for another second with 1 newton, it would be going 2 meters per second. Okay, I think you can see the logic there. Okay, so here's the easiest type of problem I could give you on an exam. I probably will give you a question like this on the exam, because it says a standard 1 kilogram mass is attached to a compressed spring. Okay, so there's your 1 kilogram, and the spring is released. If the mass initially has an acceleration of 5.6 meters per second squared, the force of the spring has a magnitude of 5.6 newtons. Kilograms, meters over seconds squared. Done. Now, I'm a little flippant about calling this a dumb question because I realize that we talked a lot about springs. We said the force of a spring is, due to minus kx. That's Hooke's law. We also derived that the energy that a spring is holding would be 1/2 kx squared. So that would be the elastic energy. So when you see this problem, you might think to yourself, oh my God, okay, what do I have to find here? Do I have to find K, and then I'm going to find, E, and maybe I'm going to take the derivative of E with respect to X, or I don't. So yeah, you could psych yourself out on a problem like this, but this one is there are going to be some questions on the exam that are just straightforward, me seeing if you know the most basic definition. So this one is the most basic definition type of thing. Okay, let's go one harder. So F net means that you're adding together all of the forces on an object, and that's what causes acceleration. So in this case, it says we have a man who's weighing 700 newtons. Okay? Weight is the same as the force of gravity, 700 newtons. He is accelerating upward. Okay, so his mass, by the way, how would I find his mass? Well, that would be 700 newtons divided by, 9.8 newtons per kilogram. Okay, so that would give you his mass in kilograms, because the force of gravity is equal to m times g. Okay, and so it says he's accelerating upward at 4 meters per second squared. The force exerted on him by the elevator floor is, okay, so he's being pushed down by gravity, pushed up by the elevator. And since he's accelerating upward, we know that normal force, the force from the floor on his feet, has to be bigger than 700. How much bigger? Well, let's see. We have F net equals, it's going to be the normal force pushing up minus the force of gravity going down. So if F net equals ma, I could go ma equals F normal minus, and then here I'm already given this, 700 newtons. Okay, so I have m, I have a, I have this as 700. I just go ahead and solve for my normal force, and I'm done with that problem. Here's another one, a little bit harder, but let's read it and try to recall what the key piece of information in this type of a problem would be. It says, A block of mass m is pulled at constant velocity along a rough horizontal floor by an applied force as shown. The magnitude of frictional force is. Okay, well, let's try to see what all of our forces are. I will draw my block as a dot. What forces do I know? Well, I know I've got to have a force of gravity. What else? Well, they give me the tension force here. And that tension force, I can think of it as acting in the x and y direction. This part of the force that's in the x direction, would be t cosine theta. This force in the y direction would be t sine theta. Okay, so I've got a gravitational force, t. Now, there's also the rough horizontal force, so that tells me that I'm going to have some force of friction. And the force of friction opposes the direction of motion, so if I'm pulling in this way, the force of friction is going to be the other way. So there's my force of friction. And what else do I have left? Oh, the force from the floor, the normal force. Okay, so there is my Fn, my normal force. Okay, now, what am I going to do to help myself? Well, take a look at this. It says a block of mass m is pulled at constant velocity. Okay, what does constant velocity mean? It means a equals 0, so F net equals 0. And that's going to apply in every direction. So, for instance, in my y direction, I would have the normal force plus, this is pulling in the up direction, so that would be t sine theta. And then my gravitational force is going down, so that would be minus Fg equals. Now, it would be F net equals ma, but in this case, I'm not accelerating in the vertical direction, so I would say it equals 0. Same idea in the x direction. In the x direction, here's my x direction and my y direction. In my x direction, I have my t cosine theta, and then my x direction in the minus direction is that force of friction. Minus force of friction equals 0. Okay, so we want to find out what the magnitude of our frictional force is. That's this. I can just bring it over, and I have t cosine theta. All right, so that's that. The last one I want to look at with these sort of easy force problems is just thinking about, it says a ball with a weight of 1.5 newtons. Okay, so you put it on a scale, and it has a weight of 1.5 newtons. That is the force of gravity. Okay, that's mg. Now, you throw this ball at an angle of 30 degrees, and it makes some arc before it comes down. Okay, so that is your projectile motion. Initial speed of 12 meters per second. At its highest point, the net force on the ball is, well, let's think. What force is acting on the ball all through its projectile motion? In fact, there's only one. It is just the force of gravity. So at the very top, it continues to be pulled on by the force of gravity. And so the force of gravity that is pulling on it is that 1.5 newtons, pulling down. So there we go. I know that 9.8 looks pretty tempting. Try to avoid it. There's also some flarf in this problem because, that 12 meters per second looks like it should be used. The 30 degrees looks like it should be used. So I know, if you don't know anything about physics and you're just taking the test, you might use your well-practiced test taker brain and think to yourself, aha, I want to get the answer that's longer than all the rest, because that's the one that's different. But in fact, we've been a little clever about this question and have preempted you from winning using test-taking tricks. Okay, now this last one is Newton's third law, and this just says if I push on you with 10 newtons, you have to push back on me with 10 newtons. Every force is paired with a buddy. And the famous example that I gave a couple months ago was this horse-wagon paradox. If the horse is attached to the wagon is pulling on the horse just as hard as the horse is pulling on the wagon, how is it that they can accelerate? And the answer is because you have this other big mass around. So if you have just the horse and the wagon hanging out in outer space, and that was it, the paradox would be not a paradox, it would be true. The horse and the wagon could not just accelerate without something else to push off of. But in fact, what happens is that the horse, so let's call that F1, the horse, and, whoops, didn't mean that. I meant the wagon and the horse are pulling on each other the same amount in opposite directions. And then the horse is pushing off of the earth, so the horse is pushing on the earth. Let's call that F2. So what do we have? The net force on the wagon in the x direction is just the force from the horse. The net force on the horse is the force of the earth minus the force of the wagon. But it's still a net force in the forward direction. On the other hand, the net force on the earth is backwards, and ultimately, the reason why you can get this kind of motion and you can walk so comfortably around the Earth is that Earth has much, much, much more mass than you do. So it has a lot of inertia, you don't. And so it's able to soak up all of these extra forces without any trouble. Okay, so what next? Well, the next thing we talked about was the idea of work and energy. So we assign a number that relates to the motion of the object. We call it the kinetic energy. It just is 1/2 mv squared. What are the units? Well, you'll remember that the work has something to do with the amount of force dotted with the distance. So applying a force over a distance is what changes the kinetic energy of something. So a Newton times a meter, a kilogram meters per second squared, times a meter gives you a joule. Okay, so force times distance gives work. Work has energy, units of energy. It causes changes in kinetic energy and has units of joules. So to state it again, the doing work on an object will cause it to speed up or slow down. There is an extra little detail here, which is that it needs to be a force that's in the direction of the motion. Otherwise, it won't cause a change. So if you have this is what that extra cosine of phi comes from. But if you just have force and distance in the same direction, cosine of 0 is just 1, so that term goes away. And then the last thing to realize about doing work on an object, if an object is going this way and you push on it in the same way, it will cause it to get faster, so that's positive work. If you have an object going this way and I push on it the other way, that will cause the object to get slower, that's negative work. And the net work just has to do with the total change in the kinetic energy. So if you start out with one kinetic energy and with a different kinetic energy, taking the difference in those tells you how much work has been done on your system. So let's look at an example. So this problem really wouldn't, you could think of it in terms of the work energy theorem, but it really is just doing a sort of definition of kinetic energy thing. So it says an 8,000 Newton car. Okay, so the force of gravity, which is m times g, equals 8,000 newtons. So the mass is going to be around 800 Newton, or 800 kilograms. So I would have to take 8,000 divided by 9.8. Okay, so it's originally traveling at a speed of 12 meters per second. Horizontal road, when the brakes are applied, the car skids to a stop in 4 seconds. How much kinetic energy does the car lose in this time? Well, if at the end, so if my initial speed is this, my v final is 0, okay, I could just calculate out my 1/2 mv squared, and that's all this question is really asking me to do. It's asking me to do this. Of course, if you're interested in how much it loses, you're going to get a negative number if you take your work equals 1/2 mv final. This would just be 0 because the v final is squared, minus 1/2 mv initial. Okay, so this would be the negative work that's been done on the car by the road, and okay. So that's the simplest idea of kinetic energy, just 1/2 mass times speed squared. Now let's look at the simplest possible version of work. It says a 2 kilogram object is moving at 3 meters per second. A 4 Newton force is applied in the direction of motion and then removed after the object has traveled an additional 5 meters. Okay, so then work equals force times distance. They're in the same direction, so that's just going to be 1. So 4 newtons times 5 meters equals 20 joules. Done. Now, something to notice is that there's a marvelous internal consistency about physics. So you could have done this problem effectively not using this formula at all. You could have done it by using your F equals MA, find what your A is, then you could use, for instance, V equals AT plus V naught, and you could find your final V, your initial V. Then you could go ahead and you could find your T. Yeah. Yeah, this would be, this is definitely the wrong way to do it. You could use something like AT squared plus V naught T plus X naught. Okay, so you can find your T, find your V, and then you could use your work equals 1/2, or your kinetic final minus kinetic initial. So you could calculate your 1/2 mv squared minus your 1/2 mv squared initial, and you could find your work that way. Okay, so there is another way always to do a physics problem, but that's definitely the hard way. This is the easy way. But again, if you're stuck on a test, it's definitely a good idea to write down as much as you can to get some partial credit on that. Okay. Work energy theorem. The velocity of a particle moving along the x-axis changes from v initial to v final. For which values of v initial and v final is the total work done on the particle positive? Okay, so we have that the total work is your final kinetic energy minus your initial kinetic energy. So if you have done positive work on an object, that means its kinetic energy at the end is bigger than its kinetic energy at the beginning. How do you get that to happen? Well, you get that to happen by being by going faster at the end than you went at the beginning. So let's look. Are there any of these cases where we're going faster at the end than at the beginning? Initial, final, slower. Initial, final, slower. Initial, final, slower. Initial, final, slower. Initial, final, faster. Okay, got to be this one. Now notice that's a little bit callous, because you notice there's a difference here between going backwards and going forwards. And so there could be a lot of detail obscured in this type of thinking about a problem. You know, in this going from a -2 meters per second to a -5 meters per second, I could have just had a nice push in the negative direction that caused that to happen. On the other hand, I could have had some negative and some positive work where sometimes you're pushing it in the forward direction, sometimes you're pushing it in the backward direction. The concepts of work don't really give you that kind of information. It obscures a lot of the details. And that is not a bug, that's a feature. You know, it's a way to simplify our thinking about these problems, which is always kind of the name of the game. So here's another example. I say a 75 kilogram. So this is another one of your short answer questions that's on your review that will also be in effect on your exam. It says a 75 kilogram astronaut in deep space is motionless. Okay, so V naught equals 0 relative to the spacecraft, and has 2 jet packs on his spacesuit that can provide a force to push him back toward the spacecraft. Each jet pack pushes the astronaut forward with a force of 15 newtons, but they are offset from one another by 30 degrees. Okay, so here's the story. You've got a force and another force. The forces have the same magnitude. They're both 15 newtons, and they're offset by 30 degrees. Now, the total net force that astronaut will experience is going to be the vector sum of those two. Okay, so this is your F net. And so, you know, when your astronaut turns on the jetpacks, they're going to experience something that's not just 30 newtons. It's going to be something slightly different because these are not perfectly aligned. So it says, if both jetpacks are engaged, what is the magnitude of the net force on the astronaut? Well, let's see how I would find it. In this particular way of drawing it, you could draw it differently. I would find it like this. I would find, let's call this F1 and this F2. F1, I could write an X and a Y component. F1's X component would be the whole thing. It would be 15 newtons, and then the Y component would be 0 newtons. On the other hand, for F2, my X component would be 15 times, I would just need to take the X component, so that would be cosine of 30 degrees. Make sure your calculator is in degrees. And then 15 sine of 30 for the Y component. And then if I wanted to have my F net, it would be the X component of my first force plus the X component of my second one. Okay, this plus this. And then to get the Y component, it would be the 0 plus 15 sine 30. So this would just be 15 sine 30. Okay, and then if you wanted to find the magnitude of F net, how would you do it? Well, you'd have to use your Pythagorean theorem. Okay, so you'd have to use your F net X squared plus F net Y squared. And that would give me part A. Then part B asks, over what distance must the jetpacks push the astronaut before he moves at 20 meters per second? Well, the easiest way to do this is with your impulse or with your work energy theorem, where you have your kinetic energy final, so your 1/2 mv final squared minus 1/2 mv initial squared equals the amount of work that's been done. So in this case, the work would be this F net times the distance. So we know the magnitude of F net. We also know that he starts out motionless, so this term would just be 0. So you can put in the 20 meters per second right there. You can put in the mass of the astronaut, and then you can go ahead and solve for D. Okay, so I encourage you to do that problem and the other ones in your packet in full detail. Okay, now power is a very important idea. I am not going to put it on the test though, so I'm not going to do a lot in this review on it. But the idea is that how much energy are you dumping in your system per unit time? Joules per second has a unit of watts, and so that's heavily used in actual industrial applications, like, for instance, your power meter at home, which is, funnily enough, actually measuring energy. Okay, now, energy conservation is a sort of a new way of thinking about these types of problems, where now instead of forces, you think about your object trading different types of energy. So you can start out with more kinetic energy and give some of that energy to the gravitational field so that you have a larger gravitational potential energy, and then you can get dropped and get that energy back. So we talked about three basic types of energy. In this class, we talked about kinetic energy, energy of motion, gravitational potential energy, the difference between being low and going high, and then elastic potential energy. That's the difference between a spring being unstretched and a string being stretched. I should show you it this way. Okay. Now, the reason why this is useful is that if you have a situation where you have not a lot of inexplicable losses, so like heat losses and stuff, you can add up the total amount of energy at the beginning, and it should equal the same amount of energy at the end. So let's look at a couple of quick examples. So a wound spring of a clock possesses. So this would be potential but no kinetic energy, because this wound spring is holding elastic energy that it is going to give up and transform into kinetic energy as the clock unwinds. Okay, let's see another type of problem. In this problem, it says the long pendulum is shown is drawn as the ball is risen to 0.5 meters. It is then given, so it starts here, and then you give it a little push. It gets given an initial speed of 3.0 meters per second. The speed of the ball at its lowest position is. So, what do you do here? You've got to add up the types of energy at the beginning and set it equal to the types of energy at this point. So if you choose your height nicely, where this would be a height of 0, and this initial height would be 0.5 meters, you can set it up such that at the beginning this has both kinetic and gravitational energy. So initial kinetic energy plus that gravitational initial equals at the end just the kinetic energy of the final. Okay, so this is at a height of, by convention, 0. And so you don't have to worry about the gravitational potential at that point. So this would be 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared. And notice I haven't given you did I give you the mass of the ball? No, I didn't give you the mass of the ball, which is important because you have a mass, mass, mass. The masses can be divided out on both sides. Okay, so now I can just use this and solve for V final equals 2 times 1/2 V initial squared plus GH initial. And I need to take the square root of that whole thing. Okay, so go ahead and stick in those numbers and see if you can get something that's close to this. I've given you the same problem once again for the roller coaster. In this case, I gave you the mass, but it turns out it won't matter in this first problem. It says a 40 kilogram coaster car moving without friction moves along a track as shown in the car. If car A starts out moving at 5 meters per second, so right here, the V initial equals 5.0 meters per second, and the height initial is 14 meters. Then it goes down, it gets faster, it comes up, it's getting slower, but it doesn't go up as high as it originally did. So at both the initial point here and the next point where I want you to think about, I'm asking how fast is the car going when it's right at that point I've identified right there. So how would I do this? I would have kinetic energy at the beginning plus gravitational energy at the beginning equals kinetic energy at this midpoint or the final for this part of the problem plus gravitational at this part of the problem. Okay, so I'd have 1/2 m v initial squared plus m g h initial equals 1/2 m v final squared plus m g h final. I guess I called them 1 and 2, so let me be a little bit consistent here. I'll put a 1 and a 2 on here. 2, 2, 2, 2, or 1, 1, 1, 1, and 2, 2. Okay, so you have a V1 and H1. V1, H1. You have a H2 is 8 meters. And you'll notice, again, the mass doesn't actually matter in this problem, so I can divide out the mass on both sides. And then you want to solve for V2. All right, and I have full confidence that everyone in this class can do that, and so I won't belabor the point. So so there's a second part of that problem, but we're going to do it on Wednesday. What have we learned about Unit 2? Forces cause objects to accelerate. With less acceleration, the more mass of the object. Types of forces can be linked with mechanical models. We did a little bit of that, not a lot. And then ultimately we want to simplify our situation by describing things in terms of energy instead of forces. Okay, so thanks for watching. Please start work on your exam review packet if you have not yet. And I'm happy to field any questions that you have. Okay, thanks for watching.